So, hello guys and girls, welcome to the computing workshop. I am the mad computer scientist and this is my workshop. Well, rather this, you're now looking at the capture of my screen here, hopefully. If this new capture setup that I've been trying to get working is actually working. It's been a while since we did something on bits for programming. It's been a lot of hardware recently. We also looked at some cloud computing and stuff like that, but not real. We haven't been doing some real programming. So I thought that we should do something. Someone suggested on the internal forums that we do some vintage programming, and we did some interesting vintage, something related to vintage computing, but also teaching some programming or going over some programming. And so I decided that today we are going to go with the learning language of choice for many people that started out college or university education in 80s or 90s, even into the 2000s. This is a language known for being very good for teaching structured programming, and it's Pascal, invented by Niklas Wirth, but then in Borland's version of this is Turbo Pascal. The one that is the famous version, if you will, is Turbo Pascal. It was devised and is also created mainly by Anders Hellsberg, also known as the father of C#. So we will use Borland Turbo Pascal in the latest release version that Borland did, which is version 7.1, and it was released in somewhere in the 90s, like 92 or 93 or something like that. This is the last version of Turbo Pascal that Borland officially released, at least I think it is. And I'm going to run this on this fairly slow DOS 6.22 system. This is running on an actual physical system, and the blurriness is caused by my capturing setup, which isn't ideal, but you'll have to live with it. So I was thinking today we're going to look at Turbo Pascal. We are going to program something in Pascal, and we are not going to do a hello world or anything silly like that. We're going to do something useful which also ties into computing history. So we are going to have a short brief on and then write a program to do what is known as a Radix Sort. This is a very common algorithm, and flashback to school days for some of you. Any computer science student should know of the Radix Sort and what it is. But it also has interesting ties to computing history, and especially punch card sorting, which is its real origins, the origins of this algorithm. So we will look at that. We will write a program to sort some numbers, and it's a lot more fun than Hello World, and it's actually a real example implementing a real algorithm. And I will also implement this algorithm free from memory. Bear in mind that I have not programmed in Pascal in quite a while. Also, I have not programmed a Radix Sort in even longer. So I will take this from memory, and the method will probably be completely inefficient and ugly. But it will be what it is. Hopefully we can manage to sort some numbers, because I hope I remember enough of this to actually be able to make it work, sort of. So Let's begin by looking at the program. Now Pascal is, like I said, it's a programming language. It's a structured programming language. It's a compiled language. Compiles down to an executable, to machine code that you can run. And Turbo Pascal is Borland's version of a Pascal IDE, or integrated development environment, where this language is central, but then there are tools in the IDE, sort of like the Visual Studios or whatever of today, but a bit more rudimentary. So in this Turbo Pascal installation, you have the bin folder. We'll list the contents of this folder. There's a lot of files in this. What we are interested in is the editor itself, and it's called Turbo. So here we have it. This is Turbo Pascal, the editor, as you can see, and within the editor you have a bunch of dialogues. At the bottom you have the function keys doing things like compiling. You can run a make command, you can open a file, you can save a file, you can also bring up the excellent help, which I will hopefully show now by pressing F1. Here we go. So here you can have a context-based help, and you can read through this any time you want. You could go into various topics like this. You can press here and look at all of this. You will have in the editor, you can see here also in the help that it also says you have the clipboard, you have undo, redo, copy, clear, a bunch of editing commands, which is very powerful. And it opens up to a blank PAS, a source file. This is not a tutorial on learning Pascal, basically because I don't care for that. You can just follow along, and hopefully we'll pick up something on Pascal. And Pascal is a very nice language still. I think it's a nice language, and it's also a compiled language, so it's reasonably fast. There are some famous games even of the PC written in Pascal. Yes, Jackrabbit is one of them, for instance. Now if we look at, let's go back here. You have the top menu where you have your file menu. These are where you work with your source files. This is for the editor. You can see the shortcuts here as well. You can undo, redo. You have all the standard editor commands like cut, copy, paste, clear. And you have the clipboard as well, where you can have several copies in a stack. You can search in source files, you can search and replace, you can go to specific line numbers, so on and so forth. This is for the debuggers. You can run, and you can step and trace. You can run to cursor, and you can set parameters for running. This is running in a controlled environment, so this means you run in the debugger, or you run with the debug activated. So if you do this, Control F9, you will load the program into memory in a compiled executable form, but with debugging symbols, so that you can set watch points and so on, and look at the code. I will show you this later on, how to do that. And then you can step and trace just like you could in a modern IDE. Under the compile menu, you can see here it has destination memory, so right now it compiles to memory. If we change this and we go pressing enter and we go back to compile, now you see the destination is disk. So either your program will end up on your hard drive or floppy if you are running from floppy drive, or it will end up in memory. Then you have compile, which is Alt F9. You have make, and then you have build, which in the build option will build. This will compile the single source file. This will create a make list, and the build will build the full program. You could have several modules spread over several files, for instance, and this will invoke linking them together. And then you have the debug menu, and here you can set up your breakpoints. This is for this menu, the run menu. So when you're running in a controlled debugging environment, when you're running, when you hit a breakpoint, you will get back into the IDE window, and that line will be marked. I will show you this later, and then you can do the step and the trace to see what is happening while also monitoring these. So Control F3 is the call stack. This is the list of the functions and calls that was made in the code before reaching the point where it is now. This is very good for finding errors. You can see the stack used to reach the point where you are now. You can do a register watch. You can list the registers. These are the CPU registers. You can look at those while the program is running and while you are stepping through it. You can set up watches, which is variables or expressions that you want to keep track of. Let's say you have a numeric variable, a value in the program, which is stored in a variable with a definition of, let's say it's called my variable. You can set up a watch on my variable and see in the window, in a separate window, how the value changes and at different points in the program. You can also add new, here you can add new watches, you can add breakpoints. In tools you have grep, but you can also add new tools to this by altering the configuration files. Here you have compiler. Under options you have, for instance, all the compiler options, where you can say you can, for instance, include 286 specific instructions if you want. You could word align to simplify for memory. You can add various types of, and if you are compiling for production, you can turn off the debug information on the local symbols. That way you cannot debug anymore, but the program size is much smaller, and also it avoids hackers or crackers looking into your code, finding debug information. You can have numeric processing. You see you can add support for the 8087 or 8287 FPU floating point units if you want, or you're running in floating point emulation, which we are now. So a bunch of options there. You can set your memory sizes. This is the limit of the program. Here you can set settings for linker and for the debugger. Debugger has some interesting settings. You could have it as either integrated or a standalone debugging. Standalone means it runs by itself, as you probably have expected. In the environment submenu, you have a bunch of setups for preferences, how you want it on startup, what colors you want, and so on and so forth. This editor also has syntax highlighting, so if we do some simple program like, I don't know, let's try this. Sorry. So let's do this. And let's you see here that it highlights the keywords and your user words and automatically indents between begin end. You see the line count at the bottom as well. This is line 3, position 5. So this one we can do, let's just do some, I said I wasn't going to do this, but I will do it anyway. And now I got a keyboard which is misconfigured. So give me a second and I will need to, here we go. So we need something like, what the hell? Okay, so there we go. So we will write this one. So let's write, I said I wasn't going to do that, but we'll do this anyway. Just to show you what this is. Come on. Here we go. Then we'll do this. And now we can compile this program and whoop, here we go. String constant exceeds line. Now we saw the error. Okay, so we didn't compile, and that is because of this. So now works fine. And there we go. So we can see that it compiled it to disk, and it had a total of 4 lines, and the compile was successful. Now if we build it, there we go. We could run this, but let's not. And now let's introduce something else in Pascal that we can. I will show you how the debugger works just real quick. So let's do a var section. This is Pascal saying that in order to fulfill the requirements of structured programming, you have to have the program as a var section. These are your variables. So unlike something like C or something where you could do something like this, this isn't going to, this keyboard is going to okay, so you can't do that. You have to have a var section where you declare all the variables you're going to use. Let's have a nice variable called test, like this, and we list this with the type that it is. So we say that type is, test is of type integer, and type integer is a a number. It's a whole number, not a float or a decimal. It's a whole number, like 1, 2, 3, 4, 5, 6, etc. So we call it test, and we tell it that it is of the type integer. And also Pascal is a type enforcing language, so you can't just do what you do in Python or something like that, where everything can be anything. You can assign anything to any variable. A variable this one will hold a value, and we are saying that the value it holds needs to be an integer, because this is a type checking language, so it will actually check that what you're trying to put into it is an integer. So this will be done by it does compile time checking as well. So if we try to write some string characters or something into that, it will complain even at compile time. So we can do let's do this so we can show the debugger. Now that we have an integer, let's say we assign, this keyboard is going to be the death of me, I think. Let's do this. Let's type let's set this to 0 first. So there we go. And let's, after this right line, we will set the test to, I don't know, set it to something else. Let's say it's 1. Now we are saying our small little program here is doing we are saying that we have a program called test program, which begins here at begin and ends at the end here, and this end is followed by a dot showing that it's the end of this module. So this is a base structure of a Pascal program. Under the Var Declaration, you will declare variables used globally within this program. So this is the var statement. You will see later on that a procedure or a function, which is something you can call into, also have their own var segments. This is one of the things that Pascal forces, that this is a structured program. It forces you to declare any variable or values or types rather that you're going to use before using them. In the between the begin and end, the actual segment of code that is running. This is to enforce structured programming, and it is to enforce readability, and it's actually quite a good feature, if not a bit verbose, so to speak. Let's let's go and compile this program. And that works fine. So now we will add a breakpoint and a watch on test. So we will go to the debug menu, and we will say that we want to add a watch, and we want to keep track of something called test. And now it cannot access this symbol because the program is not running, but it will eventually. And then we will go to debug menu again, and we tell it we want to add a breakpoint This is a conditional breakpoint on line number 5. So we set a breakpoint at line number so here's our cursor. Set it at line number 5. You can use the cursor, as you can see, if you have a mouse installed. That actually works. So now we say that we have a breakpoint. You can see that the breakpoint is marked in a red line, and this, now that we run the program in debug mode, the code execution will stop here. So you can see what is actually going on. Now let's go to compile, and we will build, and then we will do a run, as you can see here. So we can do Control F9 for instance, or we can press run here, and now we are stopped. So you can see here that the menu at the bottom right here changed to show the debug command. So now we stopped at the line that we added a breakpoint on. So now we can do this, and we can bring up our watch list, and you remember we were watching something called test, and now we can see that at this line test is 0, and it will still be 0 after the execution of this line, because the test is we can see it will still be 0 after this line. It is initialized at 0 when first execution when execution begins, and now we will set it to 0. We will assign a 0 value. You see the colon equals sign in Pascal is the assignment, whereas the equals sign is the comparison. This is the assignment. We are assigning a value to test. So pressing F7, which is trace in 2, otherwise F8 is step over. There's a if there were a function call here, like we can trace and go into the function that is being called. A function call is a step to a different place in code. Preferably in a function case, it's to return a value. You send in some parameters or values, and you get a different value back, like a mathematical function. You get the result, whereas in a procedure, in this case, is something that is not returning a value. We will get into that when we look at our Radix example, hopefully, because I don't think I will be able to write something like that without using procedures and or functions. You will see that. But now if we go step, you will see that now test is still 0. Now we will do the right line, which we will not see. But now when we step across this one, there you can see that now, since we are having a watch on test and what happens with it, we can see that now it's changed into 1. So this is now the end of the program. We can then re-trigger the program as many times as we want, because if we keep pressing step, it will re-trigger the program. Unless we press C to we can then run, and we can do this instead. We can press run, and we can remove. Now if we go to debug, you can see here also the breakpoints. If we list the breakpoints, we have one right here. If we press delete and we remove this breakpoint like this, and now when we run, we won't break. Okay, you see? So now that was a bit of showing the debug and how to do this. We can also show the call stack here if we wanted to, and that way we would have to run the program so we can review. But now we have no call stack because we're running everything in the main program, so we're actually not stepping, and we don't have a stack in that way, in that sense. We can, on the other hand, here you can see another tool. We can evaluate an expression. We can say, while we are running now, we could do something like this. Will not work because we're not in run mode, but we can do for something we can say like variable called I is greater than or something like that, and then we can see what if the result is something. We can set the new value, and we can modify our values in great depth using the evaluate and modify. So we can alter values while the program is running on data that we have in the program. This is also very powerful. As you can see, this is a quite powerful IDE. However, it's DOS based, but it supports a lot of things like you will find in more modern development environments. And it also has a quite fast single pass compiler, which is sorry, which produces quite good and tight machine code, actually, at least decent. And it has some nice libraries as well, which you can use, like the CRT library, which allows you to write to the screen at different positions, like X and Y positions. You can use that to move the cursor around. You can write different colored text and so on different portions of the screen, like create menus, for instance. You can write basically any type of DOS program in Turbo Pascal, and it's a quite powerful structured programming language, together with this quite powerful and actually very, very good to work with development environment. I actually like the clean style of the Borland tools, such as this one. It's a very nice. You could also, if you have procedures in the code you see here, you can find a specific one of them if you have a long source code file and so on. There's a lot of editing tools as well, like the cut and paste, which works like this. We'll show you. You can do, let's say we put the let's say we want to move these two lines, and we do. Now I forgot the shortcut, but okay, so it's shift delete. So you press shift delete, and then you can do which is the paste, shift insert, like this. Okay, so then you insert the lines again. You have all of these, you can insert at different places. You have multi-line selection, hold shift, step down, so on and so forth. Lots of useful tools you can do. So you could also do multi-line selection like this, upwards or downwards. A bunch of these things you could clear. Control delete means you clear the entire block, which is also very useful. Let's say we want to do this. So we do this and we do control delete. You'll see what happens. There we go, it's clear. Or we can then undo this by doing Alt backspace or undo, and it's still selected, or we can deselect. This is quite a powerful editor that you can also control completely with the keyboard, which is good. And also, like I said, you can add other tools here if you want to. You have the messages window is default, but you could add your own tools and run within the IDE. So now I will set up. Now we will write the Radix Sort program, but first I will give you a short on paper demonstration of the Radix Sort and a short explanation of it, so that we can see what it's all about. Going back to this, I'm trying to describe. I said I was going to use pen and paper, but I actually found that I had Autodesk Sketchbook installed on this on one of my computers, so I'm actually going to try to use that because I think it's probably easier to see. Now I will try to explain the Radix Sort, which is the program that we are going to create in Turbo Pascal, and the reason why is because First of all, because I want to see if I remember how to do this, because it's been quite a long while since I did these basic algorithms. It's been a few years, to say the least, since I had to last write something like this on my own, because you know, these days you don't normally do that, even when you are full-time programming, and also because when you have a career and reach a certain point, you do much less programming and a lot more management, so it's not and in my case software architecture work, which so there's not much actual programming, so it's been a while. And then sometimes I teach at the university and so on, so I get to do some of these things anyway. But when you start as a computer science student, and most of you will probably know this, since you are probably former computer science students yourselves. For those of you who are not, one of the common things you start with are the two basic forms of programming algorithms that are key to something that in coursework is often called algorithms and data structures. And the two types are sorting algorithms and they are searching algorithms, because two of the most key components or key things that you do in information processing with computers is either searching or sorting of data. So there's a variety of algorithms in this. I've chosen to do a Radix sort also because it's historically interesting, and it shows a lot of key elements of the Pascal language, which I wanted to show off in an example that is a bit more elaborate than like a hello world thing. And it's also something that many people can relate to, even if they probably don't remember this. I will see if I remember it once we are starting to programming it, because I have no references with me here in the workshop, so it may be that I screw up and we cannot get this to work at all. But let's discuss some theory then, so we can see what we are going to build. This is always important when programming. Always try to make a visual map of what you're going to build. It may not need to be a complete software architecture diagram or sketch. It could be just this function that you're going to build, or this functionality. At least try to sketch it out, its various states, and so on, and how it works. But first, a bit of history then. There are in sorting algorithms, there are two primary types. There are some invariant types, but there's or variant types rather, that have different characteristics, a mix of characteristics. But there are two key ones, and they are the I will try to type here so you see. They are the my handwriting is even worse using this software, obviously. They apparently rather, they're non-comparative, and they are the opposite of that. So they are comparative. This handwriting is really horrible. Okay, so they are non-comparative or comparative. Luckily I work with computers, by the way, so I can use a keyboard all day, so nobody has to see my horrible handwriting except for now. So they're non-comparative or comparative algorithms. And let's see if we can get this to go away. Now a comparative, can we change the size of this pen, by the way, for some reason? So yeah, it's this slider. Yeah, here we go. So let's do something like this, and whoops, and the comparative and a comparative sort is something like you compare values as you iterate, you go over a sequence. So let's say we have a sequence of values, like we have 12, I don't know, 12, 16, 4, 3, 9, or whatever. Now, in a comparative sort, like let's say a bubble sort is a common one, you would go over this over and over again, and as you do so, you will compare the value you are looking at with the value that is next, or you would compare to some other value in the sequence based on which algorithm you're using. And in the bubble sort case, you would switch these if the value here, like when we get to 16, for instance, when we get to here, then we step up and we increment and we look at the next ones. We are looking at 16, right? And we are looking at 4 in this case, and now we can see that 16 is larger than 4. So then we decide that based on this comparison, we will move this there and this one there. So we will switch places, then we'll keep going, and then we start again, and so the smaller values will bubble down towards the start of the sequence. And now once we don't have any switches, when we go into a check on the entire sequence like this where there is no switches, we know that it's sorted. Now that is a comparative algorithm where compares are being made. Quick sort is another one of those, which is much more efficient than bubble sort, but that's not what we're going to discuss now. We're going to discuss something known as a non-comparative sorting algorithm, which Radix Sort is. And here there are no comparisons. A typical example of this, which is simpler than the Radix Sort, is a simple counting sort. Now bear with me. Let's say we have a sequence which also includes doubles, like 1, 4, 4, 9, 2, 6, 2, 11, or whatever. And so we have a sequence like this. Now this will, in a single pass, go through the first sequence. Let's say we store this sequence in memory, this entire sequence here. So we go over the sequence like this, and we count the occurrences of each digit. In this case, this is a very small subset, so we assume that we have digits that are ranging from 0 through 9. So we create a variable, a data entry that will hold the number of these occurrences. So we will have a data entry with 9 or 10 positions, from 0 to 9, and in those positions we will store a sum in each position for how many. So let's say we have something like let's say we have something called count, and in that we have, it is a count is a 10 position something. We play is a memory space like this, which contains 10 slots for the counts, and in this memory we will now, as we pass through this one single time, we do no comparisons. We just say that every time we hit a 1, we increase the 1 count by 1. If we hit a 4, we increase the 4 count. We will have a list of number of 1, 2, 3, 4, etc. Now that we know how many of each there are, we can also know that if we have arranged this sequence or this index in the right sequence, because we know that we want to start from 0 to 9, for instance, we can then do each time we can actually go through each position in this and read how many of them there were, and then we can write a new sequence out. So this one, we generate a new output sequence which says that there was one instance of ones. So we write, okay, we have an 11 here, so it's actually not 0 through 9, but let's ignore that for now. But let's say we say that we have one of these, so we know we have one of these, so we write 1. Then we are getting to 2, which we know that we have 2 of because we counted 2. So then we just do write code to write as many of those as we had counted here. Then we compare the count of 3s, of which there are none, so we write none, but then we have 2 counts of 4, which we type out, and then eventually we will get the new sequence, which is now a sorted sequence. This is a very simple type of counting sort, which is only workable on small subsets, right? So also I'm drawing these examples completely from the top of my head, so you probably don't want to run these through your comp sci teacher, because these are entirely made up based on my shady fuzzy memory. So let's just assume that this is sort of right. Let's see if we can find some eraser of some type, some distinction, and get a much larger size. We can erase everything. Yeah, this looks good. So now that we have blanked that one out, switch back to the pen. Now, I said that Radix Sort is a type of a non-comparative sorting, and that is true. However, the Radix Sort can handle, as you can see in typical counting sorts, you must have quite a small subset for this to be effective, of different values that you can have. Whereas in the Radix Sort, it supports, it can handle larger numbers, such as large integers or so on. You can also use it to sort strings or whatever, anything that can be represented by a positional notation, because this is a positional sort, which is you will see why that is shortly. Now, the history of the Radix Sort goes back all the way to the 1800s and Hollerith. So this is a very old idea. Now, before we get into how the algorithm works, the history of it, which makes it a bit interesting here as well to use as an example, because it has quite a long history, and it has to do with something called a tabulating machine, which is sort of a precursor to also sort of what IBM used to do, but Herman Hollerith invented this device, the tabulating machine, which is or he didn't really, he sort of invented the, I'm not going to say that he invented a tabulating machine, because then someone's going to flame me for that, but he was, at least he was, there was some work in that field, but let's say Hollerith was the main guy involved in this. So the tabulating machine was a machine which took records like this, the punched cards, like a piano roll with holes in them, like representing salaries or employee records or whatever it may be, and then it could run these mechanically through the machine to compute or to sort. In this case, sorting, because tabulating machine had a a key part was sorting records, at least in the later machines. And the way this was done on a typical tabulating machine, I'm just going to freebase this. So let's say this is your tabulating machine. This is a huge mechanical device on which there is a crank. Yeah, you can all marvel at my drawing skills right now, on which there is a crank on the side which sets the sorting digit, and then let's say you have a stack of these punch cards up here, and this is an unordered stack. So let's say it has a lot of 3-digit integers. Then you would have a 3-digit number. So we have a punch card with a bunch of representations, a bunch of holes in columns here, like representing the different numbers. So let's say this one had 3 holes, and this one 3, and this one 3. So this would be the number 333, for instance. And now, let's say you wanted to sort these. mechanically. You had dropped them on the floor and you had an unsorted stack of whatever this was. Let's say weekly, this was your weekly salary. It's actually quite high for that time, but never mind. Then you had, in this, you had a mechanical mechanical device in here with a bunch of stuff in it. Let's not draw that, but there was a bunch of mechanical and also electromechanical, at least later on, stuff going on here, and maybe we should do a full series on how the tabulating machines typically worked, because I know for sure that the bits archive or storage, we have one, albeit an electromechanical one, but yeah, that's a separate thing altogether. But the way the Radix sort fits into this is that this crank would shift selector that would determine which of the columns were sorted, and this is where the Radix sort comes into play, because the Radix sort is a positional sorting. So the idea is to finally arrive at a sorted stack by sorting each digit by itself, and then typically you do something, and we will do this too in this example, something called an LSD, and this is not the drug, fortunately, or rather unfortunately, because that would be interesting actually, but this is this is a least significant digit sort. So you start from this digit. What you would do would be that you would set the crank to this position, and then as you ran this through, it would stack up in shelf spaces down here. Let's say there were a bunch of shelf spaces here, one for each digit. So let's say there was 0, 1, 2, 3, 4 and so on, and all the threes, in this case, all the numbers that had the digit 3 in the least significant, in the first position, would end up in bin number 3, and so on and so forth. So this would be like constructing a sequence in a program memory, but actually very, very much physical. So it would end up here in 3, and every number with a 5 would end up here in the 5 pile. Let's say there were 3 or 4 of those, and so on. And then you would take the output from this one at a time, starting from the start of the sequence or this shelf space, and then you would stack them again on top of each other back up here. You would turn the crank, shifting to the next digit, and then you repeated this entire process and you sorted everything again. So now everything with a second digit of 3 would end up here, second digit of 5 would end up here, second digit of, what is this, 7 or whatever, would end up here, and then you would repeat this same process again and sort on this digit, and finally after that loop you would have, by picking out these in this order that they are placed, you would have a stack which is now sorted in ascending order. So this was the idea of how the tabulating machine sorted, and of course there was a human operator which turned this crank and shifted these back up fed them through the machine again and so on. So but now we can do this programmatically, and this is what the Radix sort is. You can do this now programmatically. We can see directly that we have a sequence here in memory, which we will fill up by the slots by feeding through numbers. We can also do various optimizations to this, but let's not go into that now. But you could do a counting sort on a subset to, or maybe store index values in this original pile programmatically, so on. But let's do a very naive implementation of this using a bunch of slots like this to mimic the tabulating procedure. So or the way this machine would sort it. And this is the base form of the Radix sort. You choose a digit at a time and you sort. And if you don't believe that this actually works, we can actually show this with an example. Let me just get the pen again, and let's say that you have let's say we have a bunch of digits here. Let's just take 3-digit numbers because it's simpler. So let's say we have a sequence of 3, 3, 3, and we have a sequence of 4, 3, 2, and we have a sequence of 5, 1, don't know, 1, 6, and 9, 9, 1, 4. This is a 6, by the way, maybe not the most pretty 6. So let's see, we start by sorting by this. We said we were going to sort by this, so let's say we have a bunch of slots here. So now we pick out all the ones, of which there are 0, so that box is empty. Then we pick out all the 2s. So we find a 2, so we put the 2 in there. So we put the number that had the 2, so we have 4, 3, 2. And then we find something that has a 3 in it, which we will also find, which is the 333. So we will have 333 in this one. And we find something that has a final digit of 4, which we have 1. So this is 9, 1, 4. And we have 5, 1, 6. Now this is our partially sorted sequence, like this. Now we will pick out from this, now we can go over, now we write this sequence back as our new sequence. So let's start looking at this sequence. This is akin to feeding it back into like tabulating machine or the 1800s mechanical device. We take this new sequence that we have generated and we overwrite this one with this and we feed it back. So now we sort on this digit on our new sequence. So we have 2 of these. So now we will get to the ones, which we will get in order. So we go 9, 1, 4 and 5, 1, 6. So seeing as we are iterating this across, looking for each digit, you will get them in the order that they appear. So we get 9, 1, 4, 5, 1, 6. These have 1s in them, right? Now we have no 2s, but we have then 2 examples of a 3. So we have 4, 3, 2 and 3, 3, 3, and in the order they appear. So now this is scratched and this becomes our new partially sorted sequence. Now we would turn the virtual crank again, erase this, use this as our sequence. So we overwrite this and now we do the final sort on the MSD, the most significant digit. So we now sort, we look for ones, we have none. The first one we will hit is 3. So we have 3, 3, 3 going first in the sequence. Then as we are iterating this, we will find maybe a 4, yes. So we have 4, 3, 2. Now we will hit 5. So we have 5, 1, 6, and then finally we will hit our highest number, which is 9. So we have 9, 1, 4 by putting that number in that slot, and here we have our sorted sequence. You see? So we can do this programmatically, and this one has a this one now also for all you completionists out there. Let's say also describe what this one is. A typical is the big O notation. If you're not familiar with this, tells you how the performance is of an algorithm is. So in this case, it's the big O notation of this, or it's W times n, and where W, this won't tell you much if you are not familiar with this notation, but these are used. The big O notation is sort of a virtual function used to compare the time and performance complexity of algorithms in between each other. This one has a complexity. This is just for completion. We can say that unless I am actually wrong and not remembering things correctly, I think this one has a big O notation of W times n, which is or more commonly written without the time, just like this. Where W is the word length, so this is the word length of what you are the bits, the number of bits required to store whatever you are sorting, and n is the number of items, and this will be your performance. So as you can see, that if the word length increases, the performance decreases, as well as if the number of items increases, then the performance decreases proportionally. But this is this is my, as good as you were going to get from me, a description of the Radix sort, taken completely freely from memory. But at least but at least we will look at how this looks in code, and we're going to write it in Turbo Pascal, as I said, as an example program. And I'm going to write this completely freely from the top of my head, so the risk is that I screw something up and it doesn't work at all, but we'll see. Hopefully it works, maybe it won't, so hang on, and we'll start up Turbo Pascal and we will write a Radix sort. Okay, so now being back in DOS and in the TP folder, now what the hell is going on with this capture card? Give me a sec. Okay, let's just wiggle the... there we go. I think that's as good as it's going to get. Okay, so now start up Turbo, which is our editor. Now, as you can see, what we want to do is create I want to create a new file. So we will take file new. Sorry, we don't need that. Still a bit rusty here. Let's save this no-name.pass into something else. Let's save it in the. Let's not use the bin folder. Let's save it at. I don't know. Let's go up a level. Sorry. Up a level and go into TP. There we go. Go into Turbo Pascal, and in the root of TP here, so we save it, and let's just save it as radix.pass. We hit OK. Here we go. So now we have it stored in radix.pass, which is our okay, so now we have started Turbo, the editor, and we have brought up once again the capture quality is a bit weird. It's a bit blurry in this VGA splitter, but I think it's quite okay. Now, as I was saying, we are in the in Turbo Pascal, and we have created a new file. From the file menu, we have named it radix.pass, and now we are ready to start trying to write a Radix sort according to the beautiful sketching I just did, and also this will also probably be a very naive and completely weird implementation of this, seeing as I will do this freely from memory, and it's been quite a while since I had to do this on my own. So bear with me for a sec. Not only has it been a while since I wrote in Pascal, it's been even longer since I actually had to do a Radix sort implementation. So we will do I think I will do a bucket-based one, based on the ones that we have a bunch of buckets, like the example you saw me draw with the tabulating machine, where we sort into buckets, one for each digit, and then to keep it simple and to avoid messing things up, hopefully, let's say we will only sort sequences of 3-digit integers, so 006 or 421 or something like that. So everything has 3 digits, and it has 3 positions. And to keep that would give us some constraints, which would probably keep this simpler, because now the target is also to show you some Pascal code and not really go into the most ideal implementation of this type of sort. So let's start. So we always start with program, so we write program Radix. This is the name of the program in Pascal. Everything starts with the name of the program. Now I will put in this begin and end already, but let's move these down, because before we begin the program, since we're going to do this in a single compilation unit, we have some procedures. A function and a procedure. I think we need a function as well to return. You will see this shortly, but I think we need to figure out which digit is which. And I know only one good method of doing this. There are probably other methods, but let's use mine because I'm the one writing the code. Let's say, first of all, I want to show you something in Pascal known as the type command. This is like in C, where the type def. So to simplify, I think I will do something like this, and I will say that I have a type called tNumberList, and this is just an alias for something. So I say that this is an array. An array is the sequence in memory that we are talking about, and if you have programming background, you have seen arrays before, or a vector in C lingo. This is a sequence in memory of a certain type, so there are multiple slots where you hold single pieces of this value type. So however, in other programming languages, these are numbered 0 through something, so you have index 0 is the first element, whereas in Pascal supports something like this. So we do this. So we say that Pascal is an array starting at, note that these lines are ended by a semicolon, which is not always the case, because in Pascal the statement itself needs to be ended by a semicolon, and sometimes the statement is continued over several lines depending on the type of construct. But in this case, we say that this is an array which starts at index 1, or the index values. The valid values to find a certain slot in the sequence is 1 through 10, which corresponds very well with the numbers that we are going to store. Given that we are going to store 10 different numbers. This is not the digits that will be in the numbers. I'm thinking that I will use this to store a list of unsorted numbers, the list that we are going to sort. So we have a maximum of 10 numbers, and we call them 1 through 10. So we index them with 1 through 10. So we will have a support. Also, another constraint that I just invented is that we will have a maximum number of 10 numbers. So some constraints here, but that's to keep this a bit more simple. So then we have the Var Declaration. We discussed this before in our Hello World example program. Here we have variables used globally, and here I will already put down some variables, I think, like this, of this type that I just specified. So I will call this test list, and I will use it to store to later do a test of the sort, because I actually don't feel like manually there's a lot of statements just for inputting digits. I will just do a hard-coded list for now, just to show that the sorting is actually working. So let's just do something called test list here, and to loop that list we will probably need something like this. So we call it, let's say this is an integer for now. These will be used much later, but first what we need first, I think, is that we will write a comment. This is a comment in Pascal, by the way, this character. So it begins and ends like this. This is a comment block. So here everything in between, it will not be compiled. This is comments. So I will write here that we assume a 3-digit number like this. Now we need something where we can send a number and a position to derive what the number is at that position. So for instance, in 347, since we're going to be sorted by 1 digit at a time, we will store the number as 347. So the computer will assume the integer is 347, but we need a mathematical approach to finding out that the second, for instance, the thing at position 2, the second digit of 347 is 4, for instance. And this is a bit trickier than you think, if you think about it. But the way I do it, there's probably other ways, but the way I do this, not necessarily because I do this every day, because this is the way I remember how to do this. Let's write something called a function, and a function is something that takes an input and returns a value. Here we have now there's a mix of the mix here is for people not that experienced in programming, and also for you who are experienced in programming. There's a bit of mix of content and approach here, but just bear with me. It should be similarly entertaining for all groups of people, especially if I screw this up. That will be very entertaining for you, not so much for me. But let's see. Let's write. Let's call them num and pos for number and position. So we want to send the number and the position of the digit that we want. Okay. So this is also a bit weird. If you come from C, you would have done this and you started this. But remember, now we're in Pascal, so we end the function statement. But then we say that the code of this function begins here and ends here with begin and end. And note that this end actually has a semicolon instead of the period. Like I was discussing before, the program will then begin down here. So this function will belong to this program module because it's inside this declaration, but the actual code of the program that will then be executed, something like the main method in C or something, will only begin down here. So now we are declaring functions within that to be used by this program. So now we are saying that the function has a begin and an end, and this end that is not the program end ends with a semicolon, while the program itself, the module itself, ends with a period. So this is a semicolon. So that now Also this weird semicolon before begin and end, which is hugely annoying if you have a C background, but this is the way it is. So now we declare that there is a function called getDigit that takes a number and a position, and those are integer values. And now in between here, this is the code of the function. The purpose now is, like I said, to find the value of a certain digit. So now we can do something called a case, and this looks like this. So we say that we want to look at the position value. Let's do, I don't know, let's try this, see if it works later on. So we say that if it is a 1, we want to set our result. We will have we need to have a result variable, I think. So let's do a var segment. Remember, all your variables, even those used within this function here, has to be declared in the function's var scope. And those will then only be usable within these begin and end blocks. This is how Pascal forces structured programming, and really forces structured programming. It forces you to tell you already before the actual block, as the actual code block of the function, which variables you're going to use. In this case, I'm going to use a var called res, and that is of type integer, and this is the resulting number that we want to return. So if pos is 1, now comes a bit of math, and remember, colon equals sign is the assignment. So now to res we assign, this is a very common Pascal pattern to set this to res. You will see why later. You set a variable to the result if you have multiple possible results. So if you do, let's say now we can see that position 1, and this is mathematically true, that, and this is the way I used to do this. So we say that num at an integer division, meaning no decimals. So num divided by 100, if there's 3 positions, we know that position 1 is the most significant digit, so that is num integer divided by 100, and then we take the modulus with 10. This should give us the actual digit. If you, I will not explain why this is, but if you, this is the method I usually use in the very rare occasions where I have to do something like this, but this actually works fine. And if you need more positions, you can see that this is also the thing to divide with here is 10 to the power of number of digits, sort of. So if 1000, it will be 10 to the power of 3, for instance. Apart from the first one, we will see that later on. So I will show you. So we just do. Let's do all the other positions. It will look something like this. So in this case, with the same principle here. So we take. So now we do a division with 10, and then we mod with 10 to get rid of the everything. We want to get like 2, not 12, for instance. So we do this, and then we do again like this, and we say that we. And this is the special case is when you reach the LSD, the least significant digit, because this will already now you just do this, okay, and you get the digit. So if you divide, if you take the modulus with 10 of the entire number, like 447, you would get 7. So this is the way I usually do it. If you add further positions, you could increase these. So use the 10 to the power of something to programmatically determine which divisor you need. Now this is all we need in this function, and except for now we need to end this case statement, which we will do like this. So case is actually akin to begin. This is a block, and we end it with end semicolon. But before we end the function block. Now this is also something in C you would do something like this. So you would do return like this, but that doesn't really in Pascal, and especially in Turbo Pascal like this, you do this. Normally you say that the name of the function is equal to res. The assignment of the actual function name is actually the return. When this gets assigned, it's actually what is returned to the caller when the caller calls this function with these parameters. So you do this. Now that we know how to pick out a number, now let's do the interesting part. So this, I will put a comment here. This is our Radix Sort, and now comes the part where I may screw this up. I'm thinking that I will sort this in memory, just to show you also how in-memory stuff works in Pascal, known as pointers in C, for instance. So we can do this. This will be a procedure, because it won't return anything. So the procedure does not have a. This is normally subroutine or whatever you want. You don't return anything. So we call this R sort for short, and in this we will send a var end list. We have a number list. I think I'll call it that. And there we will receive the T number list. The type is the type that we declared in our type specification. And this one will of course also have a begin and end block. Now the var keyword here is important, because this means that this is a pointer. This is sent as opposed to if it doesn't say var, this copy of the list will be local to this procedure, and then once the procedure returns the original copy that you tried to send, that one will be unaffected. So it's whereas this one will actually take a pointer to a reference to the original object, and it will actually alter the original object by typing var. So we have var end list, and that is of type T number list. This is akin to how C pointers work, sort of. At least that is my memory of it. It may actually have other implications, but I don't remember those, so I will assume that they don't exist. Here we have a number of, before we get to begin, and I think here I will declare a number of variables, and this is now I will just guess what I will need. I am guessing that I will need a temp variable. This is just based on what I remember of my previous implementations of this, and then we probably need a bunch of loop variables, and I think 1, 2, 3, counting in my head how this will work out would probably be something like this. Let's call them IJKL, just because cryptic, confusing variable names is always a good thing, right? Then we need to keep track of how many things we put in each bucket. Let's call it current bucket length or something like that. And then we need to figure out which one is the next number to put back. So something like this. Okay, next number. Like I said, cryptical names is always good. And now we need to keep track of the sizes, and to keep this simple, we need to keep track of how many elements are in how many of each that there are. So let's say index of zeros, index of 2s, sorry, index of 1s maybe, index of 2, index of 3, index of number 4s, index of number 5s, and index of number 6, index of number 7, whoops, 7, and index of number 8. As you can see, my coding practices, it's not like I am following Code Complete or any other reference book in how I structure my code or name my variables or whatever. So sorry, Uncle Bob, Robert, sorry for not following your excellent advices. I usually rarely do, even if I should. Let's see. So we have a bunch of variables here, and I think from the top of my head this should work out the way I want it to. Now of course it may not, and then you may all laugh at me as this falls apart, but I think this would be the one we need. This is of a type integer, and then of course we would need, I think these are all integers. I will make them all integers now, and we'll see if I screw up. Let's say we have a bunch of buckets, because I think we will call them buckets, but we can call them shelves or shelf spaces or whatever you want, but this is where we will put the occurrences. So let's say this is an array, and this is definitely an array because it's a sequence. And for this, let's say this, now there will be a weird structure, but I will say this is from 0 to 9. These are one bucket for each digit, as you can see. This will hopefully become clearer to you once, because this is what's moving around inside my head right now, which will hopefully become more clear once it gets into code form. Right now I think I will do this because I had already declared this type. So let's say it's t-number list. So now there will be 0 through 9 indexed sequence of lists of numbers, and t-number list itself is a list containing 1 to 10 numbers. So in the special case scenario that all numbers, all the 10 numbers that we enter have the same digit, they would all end up as the exact same list in one of the buckets corresponding to that number, but it will be 1 to 10 instances of numbers, and they will end up in the bucket, the memory space corresponding to storing numbers that have that digit in a specified position. That's the idea in my head right now. Yeah, so first, no, let's first, what the hell? Okay, so first let's, so what do we want to do? Let's first speculate a bit on that. And now I'm actually live coding, so bear with me here. I will also write some comments of what I'm thinking out loud. I think out loud in comments. That's actually scary. Sorry, there we go. So each digit, with that I mean that I want to start looking at, like we said with the crank, I want to replicate that. So I want to start to look at digit number 3, because 3 would be the LSD, the least significant digit. So let's do a loop, and a loop. Now I will use this I variable as I was thinking of before. So let's use that one, and we say that it's 3, and then we use the Pascal construct called down to 1. And now we're saying that we will do something. We will initialize I to 3, and then we will do things when it's 3, 2, 1, and this means that within the loop we cannot change the value, we can pick it out, so we can use this as an indexer. So now we'll go into a loop for 3 times, starting with I being 3, then being 2, then being 1. So we will iterate over this block of code 3 times. Okay, and being a for loop means it also needs this begin and end block, like so. And okay, so now we need to initialize our we need to reset our values so every iteration. So this will be a bit of boilerplate code. I will just write it out and you will see what I do. So we set them all to 0. I think this should make sense, maybe something like this. Sorry. We also get a nice nice view, nice insight into my rather confusing thought process as I do this, which could be a scary experience. So let's do something like this. We set them all to 0. This is of course a non-efficient way of doing that, but let's ignore that for a moment. So now this is the we're still in the for loop. This is one of the issues with Pascal, keeping track of the begin and end blocks, because it's not always clear where you are. But now we haven't closed the for loop yet, and we actually won't, because now we did close the for loop. Sorry, it's down here. So we're in the for loop still. Now we step through the list as it is now, I think. Let's just write that down so I know what the hell I'm doing. Like this. So we step through the list as it is now. And then, so we have 10 numbers, and we said that the number list is 1 through 10. Remember, it was indexed with number 1 through 10. So we use another loop variable, I think. Let's do something like this. Let's use j and do 1 to 10. Now we are counting upwards. Okay. Okay, it's Pascal, so I need to do this, right? So it needs to be do. Of course. So now we added the do keyword. So now we are going to count upwards from 1 to 10. So we can use j as an indexer. We'll see later. Let's put begin end blocks. We don't forget to do that. Now in this loop, we will use our getDigit function to get the digit at this position where we are at now, the outer loop, the first one, 3 down to 1 that we wrote. We will take that I value, at least I hope that this will work out, this section of loops. So now we will go through each number in the list and we will pick out the digit corresponding to I, which will be 3, 2, 1, and send it to our getDigit function to get the digit at that position. So, and that is where I will use the temp. So we will get the digit like this. I'll just write this down here. Get digit and place in the right bucket, because we want to place it where it belongs. So let's use the temp for this. So let's say that we assign temp to whatever it is for each number. So now for 1 to 10 we do this. So we get So temp is equal to get digit. Now we call the function, so we will go into the function. Now we need to provide it with the values, and the value is nlist of j. Why is that? Because we take nlist into this procedure. This is the list of numbers. Now we want to keep working on the same list and send the go over the list, and then we need to overwrite the list with the contents of the buckets, akin to putting it back on top of the sorting machine and then running it through again, so now we go through each number. So nlist of j is actually a number at position 1 to 10, so this loop will go 1 2 3 4 5 etc. up to 10. So now we want what is at position 1 2 3 4 5 etc., which is our list of numbers. So I do this, and for position we want to send I, and I is the outer loop, so we will have 3 2 1, so this is the position. So we send the number, let's say index 4 held number 447, and we sent an I, we was at the second outer loop, so we have position 2, and we have nlist of j is 447 and I is 2. And that would give a call to get digit for what is the second digit of 447. So now that we have these values, we can then do, let's do another case. We'll do something like this. We could do something like this. This will be a lot of boilerplate code, but we also need to end the case statement, and in between we check what the digit is. So let's say we have a bunch of statements here, and we have multiple statements, so we need to have begin and end underneath these blocks here. And for the 0, now comes the code where we enter this into the correct buckets. So we remember we had something called buckets. So here we take temp, which is the value, like 7 or 6 or 2 of this digit at this position. And remember, we created a sequence of which we called buckets, which held positions indexed by 0 through 9. So this means that once we hit like a 7, we would compare it to see what we will find, and this one contains, each position contains a separate T number list, a separate list of 1 through 10 numbers. At least this is my initial idea, and this way we can now figure out what the next index is. Okay, so since we initialized all of those at 0, that's probably a stupid idea, but let's ignore that. Let's say I0 plus 1. So since this one started at 1, it's 1 through 10, we do this. So we have the index, we want to know what the next index is, where we want to place the value. So we want to place it in the T number list at the value of the next empty element. If we are filling up the bucket, we want to know what the next empty slot is. So we do this, I think. So we set that value with the assignment operator, and we set that to nlist of j, which is the value that we put the whole number, like 447, not the 4. So now we can do. Now we need to increase the next, what is the next slot in that bucket's number list that we want to use next time if we find another one. So we do assign I0 to I index of 0 plus 1, so we increase it with 1. So next time it will be at position 2, because now we put it at position 1 because it was indexed at 0. We could have started it at 1. It would be much simpler, but I don't have the strength to rewrite all that now. So now we need to do all of this for all of them. So this will be a bunch of repetition going on. So bear with me while I do this. So this will be for all the cases. You can probably fast forward this part if you want, because this will be boring. It's a boilerplate code of the same thing, really. So let's do this, and then I 1 plus 1. We assign it to n lists of j. Sorry. Like so. There's a bunch of these. So for each unique case, this is very, very time consuming. Let's see if we can use the copy paste command. Let's do this, and we do edit, we do copy, and then we do paste, which is shift insert. Okay, that makes life a bit easier. So we change just a few of these. So we change them to I2, and we do I2. I'm just gonna type this boring stuff. So which one was paste? Shift insert, yeah. Okay. So now we are at 3. If it's a 3, I suspect that there is a better way to do this. On the other hand, let's do it this way, because this is the only way I can think of right now, because it's late in the evening and I have not had very much coffee today either. So let's do it this way. This is the boring way, and probably a much more efficient way of doing this. But yeah, let's just do it like this. Something like this. Okay. So the idea is to increase the next available slot in this bucket, or rather this bucket index, to be able to insert at the right place, right? At least that's what I'm thinking right now. So let's say this is I6, and this is I6. Go. Isn't it lovely to have these unedited videos where I just boringly insert code? However, all of you Bits members, you're probably used to this by now. Any YouTube watchers, bear in mind that this is about as good as it gets in these videos sometimes, and it's equally boring for me as it is for you watching this, I assure you. But it's just that I can't be arsed to come up with a more efficient way of doing this right now, because my brain is screwed. So not really I'm not exactly feeling rested and fresh, so this is as good as it's gonna get. So let's make sure we had all the cases that we did, and now we also need to end the case statement, I think, because I suspect that I didn't do that. And now we get into this begin end hell. Okay, let's scroll through this, make sure we had everything. So this is the end of the case statement right there. Okay, so we had all the cases. Now we have sorted everything into the buckets. So now we have to go out of the we need to get back into the outer loop. So now comes the hell of figuring out which one is the outer loop, right? Let's see where the hell we are. Where is the outer loop? What the hell? So we need to get back into the somewhere there, I think, or I will be completely wrong and we're actually in the wrong position. Let's see, where the hell are we? Somewhere here, I think, will be the right place, or I am completely wrong, because we want to be before the end of the outer loop, and I think this is the end, the outer loop. So now that we have sorted it into buckets, before we go to the next digit, turn the crank if you will, we want to set this variable I created before, because I knew I was going to do this. Hopefully I'm doing it at the right place as well, and hopefully my initial thinking actually holds up, because that's not entirely certain. So let's say we set the variable next number, and we set that to 1. This is the next place to insert a number in nList. So we do this. So now we read, we have another variable. Let's use k this time, which I actually figured out now that we could do, because I think I had a variable called k. So let's say we go from 0 to 9. This should work maybe. So we do, and then we have to have another begin and end block like this. And now we go from 0 to 9, because now we want to go over the number of buckets, and then we want to do an internal loop. Now I'm actually getting back to what I was initially thinking. I was getting confused by my own mind for a while. So this is what I wanted to do, right? So we do another case statement. So we do so we decide, and this is also very ugly, I think. So the case has to be ended here, and then within the case this is very ugly. So we just want to now we want to reuse the count we did before to set to set the current length of the bucket. Okay. As we are, so since this could probably be more effective if you put the balances, like in the I0, I1, I2, I3 in this case, so on, into further array, but right now that just struck me that would be more efficient and probably smoother. But let's do it like this, because now I already committed to this half-hearted solution. So let's say that this is a 0. We set the current bucket length. We have this variable because this is what I initially thought in the beginning, and I actually thought of this in some inefficient way, but let's stick to that. So we set, you can also see now that you can write these on a single line. So we can say that the current bucket length is the length of what we counted to. Okay, so this makes it, we can use this current bucket length like I thought initially to be used to find the right index when we are when to stop. We want to read back the values into the original array, overwriting it. So we want to overwrite the original array. This is very inefficient, the code, but as long as it works, I will actually be happy right now if it actually holds together, because as I said, it's 11:40 in the evening and I've actually worked overtime as usual at work, so not really minty fresh. So this will do for now. This is actually horrible. Okay, so then after we have iterated this and exit from the K loop that we have, or rather within the K loop, like here, I would suspect would be the right way to do this. Let me just think for a second. Okay, so now we want to loop the number list that was in this bucket position, and we want to use the indexes called for K. So we want to go through all the buckets and read it back into the original array. So we do a loop that looks like this. So we take for L, which is also a variable I created before, and this one will actually go, I think this is what I did, I don't remember actually now, but it starts at 1, I think, to current. We'll have to see if this compiles, and it maybe starts at 0. I can't even remember what I wrote before. Let's say it starts at 1. I think that was what I wrote. So to the current bucket length, which was the number of maybe the number of 5s that we counted, for instance, that will be the length of that sublist contained at that index in that bucket. There will be a list of that many elements. So we will do this. So now we write this, and then we'd say begin and end again. So now we go and assign to our list, which is now pointed. We will change the actual list in memory, not a copy of it, but the actual list. So now we will say that next n, remember I set this to 1 before. So now we will change next n into, we will assign it what is in the buckets at position K, which is the digit bucket. So it will be bucket 0, 1, 2, 3 up to 9, and we want what is at the L, which is what we now have going up to range of the length of the list in that bucket. So if there's 6 values with a second digit of 2, we want to go from 1 through 6, and we want to add them in sequence into the original array. This is akin to lifting out one stack at a time from our mechanical machine and putting them into a single stack again. So we are using the original list, writing back to it. We are overwriting it with our partially sorted list, like I was describing in the drawing. And then of course we need to keep track of the fact that then we need to move forward in our original list. So we need to do, do this. We need to say that our index is increased by 1, so the next time we have the next position, and this should be it. Now let's inspect if this compiles, and it doesn't because something is wrong. Let's see what's going on. It's because, let's see what the hell is going on here. it's which line was it? I usually should have compiled before to just make sure that it was actually working. Let's see what is going on here. Oh yeah, sorry. Whoa, yeah, my function has, okay, I'm really tired now. Okay, so it needs to be like this. It needs to, the following, it takes two values of type integer, but it also returns type integer. Because it's a function, so you need to specify return type, which in this case, it will res is an integer, which will then be set, the value of the function needs to be set as an integer now, so it needs to return an integer. This is also enforcing structured programming, and here we go, and there we have the hell I was talking about. Okay, this is not good. Let's just complete the program and then fix all these begin end hells that was gonna. So now I will show you, before I fix everything, I will show you in this segment we will write a small test program that we will use. So we remember we had a variable, a global one that we called test list. I think it was called test list. I don't remember, but let's hard code some values that we can test with, because I can't be, like I said, I can't be bothered to. Let's just make up a few values here. Let's say our test list. These are also in the, this is T number list, so it's from 1 to 10. This is our custom type that we created, let's say 605 or something. Let's just make up a few values to see if the sorting is actually working. So these are indexes into this sequence, like 1, 2, 3 and so on. And there we can store values of this type. So let's say it's 4 maybe. Let's say this is 312. Just making up a few values as we go along. So this is maybe 063. Remember, we need 3 digits. Could of course do checks for that and add zeros, so pad it with zeros. That I cannot be bothered with right now. Let's say this one is 132, for instance. Let's just get a nice mix of values here to try out our sorting. Say test list here is index 7. Let's make up a value 406, and let's say test list with index 8 is, I know, 419 or something, and let's say that test list of index 9 is, let's make up another value, I don't know, 777, nice value, nice occult value. And index 10, let's set that to, I don't know, 397. That sounds good. Something like that. And then let's make a little test loop here. Let's say we want to test the sorting. So now this will be the actual program. So we will write something like this. Let's write out the unsorted list. So we do some sort of loop, and now we can use this test I variable I created later or earlier. Damn, I'm tired, man. 1 to 10, I think. Now the amount of the risk of error actually increases enormously with how tired I am now. Let's say this let's just write out the list. So we write test list at position test I, which is our loop variable, something like that. Now we want to do the sort. So now we want to call our rsort method, I think, and here we now send endList. This is our parameter. Remember, we took or sorry, not end list, it's test list. We want to now we want to sort the list, right? So we send that as a parameter, and now we will send a pointer to it. So we send a reference to it. We will sort, because we use the var keyword, so we will sort it in memory, and not a copy of it. So now we write a blank line just to get some space, and we do this, and we write something like this. We say this is a sorted. Now we look at the list as sorted, and then we do the same thing. We do this for test I. We reset it, so we have 1 to 10, and now we write out the same sorted list, the same list, but we write it out again. So we just duplicate the loop above. For simplicity. Now I could have copy pasted that, of course, seeing as it's the exact same loop, but yeah, that could have been done, but wasn't done, like many things in this workshop. So right, so then we just write the list again to see if it's sorted. Now let's see if this compiles, which it doesn't, of course, because I have some sort of discrepancy in the number of begins and ends. This sucks in Pascal, so let me just see if we can find this. So this is begin belongs to the outer for loop. So we have, how many begins do we have? We have 1, we have 2, we have 3. You will do this a lot in Pascal. So this, let's just start from the bottom here. Okay, so let's start from the bottom and see what the hell this is. Okay, so we have here we have these two belong together. So this begin and end. Okay, so these are okay. This one is for the loop, so that one is okay. And then this, okay, so this end right here would need to be, that is for the loop, but this one, I think, this one is for the loop, and this one, so this is the begin for the for loop. No, it's not. This is the second loop. This is outside. This is the next one. So there is the end of the second loop. Now this should go all the way back up to the first loop. This is basically hell to deal with. So all the cases are ended. Okay, so this one goes all the way back up here. So this is the begin for the 1 to 10 loop. So that is the step through of the list. So what the hell? Okay, so okay, so that is fine. This is fine. And then after the step through of the list of all the numbers, we are going to go through the buckets, which we are doing. And this end, which is all the way down here, is for something else, right? So that doesn't have, this one goes back to the next begin after the list. Okay, so this one goes all the way back up here to the outer loop. So that one is the outer loop. This one is the outer loop. And this one should be, okay, so there's one too many ends, I think. Let's clear that one, see if it compiles. And it doesn't, because, okay, sorry, because I forgot this, because I'm an idiot. There we go. That's more like it. Okay, so now it actually compiled. So now you got to see one of the bad, hellish pieces of crap with Pascal, which is the begin and end segments, and actually matching them up, which really sucks because it becomes quite convoluted. Yeah, so now it compiled. So now let's see if we make this like this, and then we actually build this. Now let's see if we can run it. So we actually built this. So now there should be a program where I saved this. So if we exit this, and yes, I wish to save this file. So now within the TP folder, we should have not at all, because where the hell did it compile? So in the bin folder we should have, what the hell, something called Radix. Oh, okay, sorry, it's because I didn't compile it into yeah, that's it. Let's open where did I actually store it? Let's see if I can get the mouse pointer to come into play somewhere. Okay, so it was stored in the root of the TP folder, and it's called radix.pas. Here we have it, and this is our program again. So let's now choose this is the idea. I choose destination memory, not on disk. So now compile, and we build it again, and now it should have built it to disk. So let's go back and let's see if it actually ended up here. There should be something called radix.exe, which there is. This is our built and linked program. Typing it in, and there we go. So there you have it. So unsorted is our unsorted list, which we set as an example, and you can see in the sorted list we actually get the sorted stack. So I actually managed to keep my brain from completely screwing up, and I actually managed to sort this properly, just hacking this together as we went along, which actually surprises me that I managed to do this. I should have screwed up somewhere. I would have expected that to happen. Actually, it didn't happen. However, the solution was in places I think quite horrible, but it actually worked on the first attempt, which is like I said, quite surprising, but given that okay, it didn't actually work, it did an oopsie on 149 and 132. You see that there? Ha! Celebrated too early there. So something went bad for some reason. So I had to make a small cut as I was already running a very long video, and I had to debug something and to actually figure out what the hell wasn't working. So I was celebrating a bit too early, but as it turns out, I think I managed to solve it now. So I'm actually reloading the program now just to see if we did this correctly, and the reason was that I had put an end, of course, in the wrong place. So this wasn't being reset at the loop, so it was actually messing up the index by not resetting this back to 1, because this end had gotten out of place. Like I was saying, this took a while to debug by looking at the changes of put a watch, like I showed you before, on the list, and I managed to figure out where things were going wrong, but I didn't want to bore you even further, so I actually cut that part out. But it was a bit of a debugging session. But now, this is one of the most annoying things about Pascal, in my view. Still, it's been a while since I've done any Pascal, but now it begins to annoy me again, is the fact that these verbose begin and end things, they really are annoying, because it's hard to get them at the right place. And now you get a feel for it. So now I sort of knew where I was going to look for this, so finally managed to find which one it was that I actually removed the wrong one before. But now I think this is going to work. If maybe, or maybe it still doesn't work. It could also be that I am completely mistaken and it doesn't work. So now let's just make sure we are building to file. So destination is memory, so that's not right. Let's compile it again. We can do make, not that it matters, but let's build it. And now we should have a new file which would hopefully work like this. What the hell? Keyboard is going bonkers. Okay, so in the TP folder there should be a new version of this file, which there is. So let's run this, and now maybe it, oh yeah, finally this time it actually worked out once all the begin and end got into the right place. So it means that I was sort of right the first time, and then celebrated a bit early because I'm an idiot and had turned the begin and ends a bit on top of each other and inside out. But now, once the begin and end segments are sorted, I think the list is actually finally sorted using the method that I managed to devise on the top of my head. So yeah, that was an awkward early celebration, but at least now this thing is working. So I managed to fix that, and now this is a working Radix sort, and we sort of did it quite intuitively, I hope. Also very long video, which it always is when you are live programming. It's long and tedious, but I hope you found it somewhat interesting. And I'm still surprised that it was just that end thing. I started celebrating, then when I saw that it wasn't working, I was thinking, oh crap, because I thought I made some sort of logical error when I was thinking this one out as we went along. But apparently I was actually I'm still surprised at this time that it was just begin and end that got messed up. I'm still surprised that the logical part held up, especially seeing how tired I am now. But apparently it did. So now the list, our example list, is sorted, and also our begin and end, the program structure is actually correct this time, which is a good idea. And you can also see that I did this in a live session and decided not to cut out when I screwed up the begin and ends, because that's part of the fun, right? Screwing things up. At least I hope so, because I do that from time to time. I try to find the fun part in it. As you probably saw, this isn't exactly a tutorial video, so I wouldn't use this as an example of anything really, except as an interesting piece of using Turbo Pascal to actually do some sort of semi-useful algorithm apart from Hello World, and actually also getting a discussion on the Radix Sort algorithm in itself. So also I felt like doing it because it's been a while since I wrote some algorithms like this one, and it's also been a while since I wrote Pascal code. Actually quite a long while. So it was fun. It was a nice reunion with Turbo Pascal on some original hardware. So it was fun. Yeah, so for now, thanks, and next time I'm in the workshop, I don't know what the hell we're going to cover, but probably something along the lines of maybe new hardware that has come into the bits collections, if I can actually manage to get my hands on it. We'll see, but we'll find something interesting to talk about. Yep, thanks, and bye for now.